In the previous video, we went over the Stern-Gerlach experiments for spin separators through gradients in magnetic fields and polarized silver atoms. So in this video, we'll talk about a similar situation through the use of polarized light. So we'll consider to start linearly polarized light, which in classical electromagnetism is defined by having an electromagnetic or an electric field vector rather that is pointing in one single Cartesian direction x here, where we propagate our electromagnetic wave in the z direction. So if our field or our wave is propagating in the z direction, then our field, electric field, is here only in the x direction plane, in the xz plane. This is for a polarization in the x direction. And if we look at light that's polarized in the y direction, on the other hand, then of course we get a very similar expression, but now our electric field is only in the y direction. So I should technically put field vectors there. So these are two linearly independent states of linearly polarized light. So we can use polarization filters or polarized filters to select either polarization or light that is polarized in the x direction or light that is polarized in the y direction by selecting only those components. So if we have unpolarized light going in, we have an x polarizer filter that will filter out only the electric field components in that x direction. And so if we then were to send this x polarized light through a second polarizer in the y direction, then no light would be transmitted, because there's of course no y component to the light that has gone through the x polarizer. Okay, and similarly we could turn this the other way around. We could take unpolarized light, send it through an x polarizer filter. We get through an y polarizer filter, we'd get y polarized light here with a y unit vector in the expression for the electric field. And if we were to send that through an x polarizer, then no light would be transmitted. So now we can take this approach and use these kind of filters similar to how we've used spin separators in the Stern-Gerlach experiment. So in particular, let's start with unpolarized light and send it also through three filters. So remember, in the case of the Stern-Gerlach experiment, we send it through a gradient, an electromagnetic or a magnetic field gradient in the z direction, then a magnetic field gradient in the x direction, and then again a magnetic field gradient in the z direction. So now we're translating that here into sending unpolarized light through a polarizer in the x direction, then through a polarizer in the x prime direction, which is at an angle of 45 degrees between the x and the y direction. And then in the third stage, we send it through a y polarizer. So if we compare this with what we had before, first through an x polarizer, then through a y polarizer, and in the end, we end up with no light transmitted. So what we did now is we added this x prime polarizer in the middle between the x and the y polarizer filters. So of course, one of the things we expect classically is that if we select out with the first filter only x polarized light, then there's no way that even with this additional x prime polarizer, there would be light transmitted. However, in reality, light does get transmitted. So why is that the case? What happens is that this second filter, this x prime polarizer, acts just the same as the x direction gradient magnetic field in the case of the Stern-Gerlach experiment. And that destroys the knowledge we have about the polarization that was introduced by this first polarizer. And this destruction of the knowledge of that property allows it then to take again on any value in this second y polarizer. Okay, so let's look at that in terms of electromagnetism and in terms of our field quantities. So we have here these three regions, 1, 2, and 3. The first region after the x polarizer, second region after that 45 degrees rotated x prime polarizer, and then the third region after the y polarizer, again back in the original frame of reference of xy. So, and in that first region, that's exactly what we calculated before in this this first example with only 2 filters. So we get an expression where we just have the original amplitude and then x0. So that gives us our field in region 1. When we go now to region 2, this component of the field along the x direction that we had in region 1, what we select from that component is only the x prime direction. The x prime direction which is rotated over 45 degrees compared to x. So that gives us our square root of 2 times this x prime direction. Okay, so you can see that the magnitude or the amplitude of the electric field will be square root of 2 over 2 times the original amplitude, or of course the original amplitude divided by square root of 2. If we then rewrite our x prime in terms of its expression in terms of x and y components, then we'll have a square root over 2x plus square root over 2 times y. So we can write in this region 2 our field in terms of our original x and y unit vectors. Why do we do that? Of course, because in the last step, when we go to region 3, that's where we apply again a polarizer now in the y direction. So we're really selecting out this y component. And if we select out this y component, then we see, of course, that in region 3 we find a field that has a magnitude that's in this case 1/2 of the original amplitude and now in the y direction. So the crucial step in this entire derivation that allows this to be non-zero is the fact that we have this intermediate step where we force the field along this 45 degrees direction, which reintroduces in some sense the x and the y components and then destroys the polarization that was introduced by the first polarizer. Okay, so there's a reappearance of this y component because x prime is not orthogonal to x and y. So we can do something similar if we were to not use a y polarizer in this case. If we were to use an x polarizer, we would get the same non-zero result. We'd get actually something that has the same intensity, and I think I'll come back to that in a little bit. And that really is an analogy of the fact that we have destroyed any measurement from the first polarizer filter. So what happens now is that this, if we draw up the analogy between the Stern-Gerlach experiment and the measurements with these polarization filters, our x prime polarizer really acts as a selection on the x direction of the spin equals plus h bar over 2, and the y prime polarizer, if we were to have used a y prime polarizer in the second stage here, then we would have, of course, found a very similar result, and this acts as a spin selector for the x component of the spin equal to minus h bar over 2. So if we then write the field in the case of this y prime polarizer, we would have found something different. Slightly different, there's just a minus sign here, but otherwise it's very similar. And again, as I mentioned just a minute ago, we can replace this third polarizer with a y direction polarizer, which was a y direction polarizer, with an x direction polarizer. And if we now go through the entire calculation, we'd find that we would see that we find the exact same amplitude as for the y polarizer, except that now our field is of course in the x direction in region 3. And so again, that indicates that the intensity of the light after the last polarizer does not depend on whether we look in Stern-Gerlach terms at the SZ equal plus h bar over 2 or the SZ equal minus h bar over 2 components. So they're just the same intensity, so we've completely lost any measurement of SZ, or in this case, in the language of light polarization, we've lost the information introduced by this first polarizer, which forced the light to go into that one polarization state in the x direction. So if we now look at our correspondence between the Stern-Gerlach on the right and or light polarization on the left here, our linear polarization in the x and y direction corresponds with having a SZ component that is equal to plus or minus h bar over 2, or spin component along the z direction up or down, and the other 45 degrees rotated reference frame in x prime and y prime, the linear light polarization along those directions is then analogous to the x component of the spin equals to plus or minus h bar over 2. Now, what we know is that in the case of linear light polarization, we can write our x prime and our y prime in terms of x and y. We can write x prime as the square root over 2x plus square root over 2y, and y prime as minus square root over 2x plus square root over 2y. Okay, so we can take this knowledge and now apply that back to our Stern-Gerlach experiment, where we can write our Sx component or two states, Sx equal to plus h bar over 2, in the same way with the same linear combinations, or with the same coefficients of the linear combination. And so we write that as a linear combination of our Sc equals plus h bar over 2 and our Sc equals minus h bar over 2 states. And similarly, we can do that for our Sx equal to minus h bar over 2 state, which will then of course pick up this minus sign here, which we get in our y prime state in the case of the linear light polarization. Okay, so now what about this Sy polarization state? So in the case of the Stern-Gerlach experiment, we could also take a field gradient through which our silver atoms go that is in the y direction, and there's no preference for x or y or z directions in the Stern-Gerlach experiment. They're all equivalent due to rotational symmetry. So can we come up with something similar, something that's analogous to this Sy component in the case of light polarization? However, there is of course another independent polarization mode, and that is circular polarization. Now, what is circular polarization? It's where where there is a combination of x and y linear polarizations, but the y component is lagging behind the x component by plus or minus 90 degrees. Okay, so that is circular polarization. There's a left and a right-handed circular polarization. In the left-handed case, we pick, I think it's a plus sign. The right-handed case, we have the minus sign. I could be wrong. But in any case, this phase delay corresponds with the negative, with the left and right-handed circular polarization, or with the plus or minus 90 degrees or pi over 2 phase shift in our electric field for x and y. So if we look at that then in terms of phasors, or we use our e to the I pi over 2 is equal to I expression, then we can actually write that as again a linear combination very similar to what we had earlier. I guess I wrote it with square root of 2 over 2. Here I write it with 1 over square root of 2. So we can write our two independent linear or independent circular light polarization states as 1 over square root of 2 times x plus or minus I over square root of 2 times y. So we've picked up this I, which turns this into a circular polarization state. Okay, and now very similar to how we've been able to write our spin states, or our x spin direction equals to plus h bar over 2 or minus h bar over 2 as linear combinations of the z spin states, so spin state z plus h bar over 2 and spin state z minus h bar over 2, or up or down. So now we can do something similar with the y direction. We can write these as linear combinations of the z up and z down spin polarization states, but instead of having a 1 over square root over 2 for the spin down component, we have an I over square root over 2. So that's because of our I that we picked up here for the description of linear polarization. So that's how the description of light polarization through both circular and linear polarization is similar in description to what we did with the Stern-Gerlach experiment. So putting this all together, we can summarize that by looking at these two main conclusions from looking at Stern-Gerlach and the light polarization. So first of all, not all properties of a quantum mechanical system can be known simultaneously. So in the case of Stern-Gerlach, we can't measure the spin direction. In the case of the polarization, we can't fix one polarization state, then measure another polarization state, and then expect the knowledge of the first one to still be valid. So there are these incompatible properties that a measurement of an incompatible property destroys the knowledge of other properties, and we'll define what incompatible and what destroys really means here. And then the second conclusion is that we can describe the states of a physical system, or it seems like we can describe the states of a physical system as vectors in a vector space. So in particular, if we go back to the description here of our SY in terms of SC components, so we can look at this as a state that is part of a vector space of different states, where we can add and subtract different states based on certain coefficients and relations between them. So there are states in a vector space with arithmetic relations between them. So what we will do is we'll take these conclusions based on Stern-Gerlach and light polarization, and we'll apply them as fundamental principles to further study of quantum mechanics. We'll come up with postulates, and we'll start from those postulates to actually study quantum mechanics. This is very similar to, for example, what happens in relativity, where we look at experiments. The experiments lead us to think that the speed of light has to be constant, and so what do? We take that concept of a constant speed of light and set it and elevate it really to a fundamental principle, and then see what we can derive in terms of physics from that principle. Note that there's a difference here with classical mechanics, in particular due to this first principle, or this first conclusion, which is that there are limits on how well we can know the state of a system. In classical physics and in classical mechanics, if we have the full state or initial state of a system, we can, through the least action principle and through equations of motion, we can determine all properties at any future time. There is no limit on how much we can know. A particular measurement does not destroy the knowledge of other properties. So that's a fundamental difference that we will encounter, and that this entire quantum mechanical treatment is of course based on. So what we will do in the next video is actually start looking at the mathematics that underlies all of this, talk a little bit more about these vector spaces and about how the state of a physical system is written down in terms of those vector spaces. So stay tuned for that. Okay.